Hello everyone, my name is Jin. I'm a PhD student and my advisor is Professor Anderson. The topic I'm going to present today is cross-domain fake news detection. First, I will introduce the motivation of this research. With the popularity of social media, people have been posting, sharing, and browsing information online more often than ever. Among all this vast amount of information, a large portion of them are actually false and misleading. During this year's pandemic, this problem has been even worse. Some people claim that COVID is a hoax and that the cure is worse than virus. There are still more fake news related to COVID on various topics, such as healthcare, politics, and gossips, which may very likely to cause people to suffer from health or economic losses. With this concern in mind, we have been developing methods to detect fake news. Before we start introducing our method, we will review the literature on fake news detection. From the diagram, we divided the methods into two ways. Based on the information that is being used, they can be divided into content, context, and network-based approaches, or a mix of them. Based on the usage of labeled data, they can be classified as supervised, semi-supervised, and unsupervised methods. Specifically, most of the work are focused on deep learning methods, supervised methods. This paper proposed a content-based method. They utilized both image and text content, but unlike other content-based methods, they convert the image into sentence, and then they use the same way to extract a text from image and original text content. Then, based on the similarity function between the features extracted, their model minimizes both classification and similarity losses. The dataset they adopted is Fake News Net, which is widely used in the literature. Here is a paper that uses both content and comment as a context. They extracted word level and sentence level representation for the news content and the word level representation for the comments. Then a sentence and comment co-attention mechanism is used to link the relationship between them. In this way, they can explain which part of news and associated comments are more important for the detection. This paper is a network-based method. It utilized users' information in a tweet-retweet propagation network. By using user-to-user mutual attention, the method is able to capture both direct and indirect user-pair relationships. The last method we want to introduce is a semi-supervised approach. It first utilized users' report to infer weak labels of the unlabeled news by training an annotator and to label all the unlabeled news. And then the reinforcement selector selects high-quality labeled news from the annotator. The selected news and labeled news together are used to train the fake news detector. Fake news detector then gives a reward to the selector based on its detection accuracy. So the selector can take an action of keeping or discarding the news from the annotator. To summarize, we listed some challenges in detecting fake news. To our knowledge, there is no method that did cross-dataset testing, which might not be good for generalization. Second, different methods sometimes use different datasets that contain various information, making it hard for comparison. Third, the existing methods seldom address interpretability, which is important in fake news detection, as people might not be convinced if we cannot point out why the piece of news is fake. Last but not least, most methods are based on supervised learning, but fake news are being generated at a fast speed, and creators are getting more and more experienced. It would be impractical to annotate a large amount of news pieces. Now we introduce our method, trying to tackle the first challenge, cross-domain fake news detection. The method is inspired by this paper, Domain Adversarial Training of Neural Networks. The structure of the networks includes a feature extractor and two classification heads, which are the label predictor and domain classifier. The basic idea is to learn to extract features that are relevant to the prediction of class label and at the same time unlearn the domain-relevant information. The unlearning of domain information is to do the reverse of gradient descent. To apply this method to our problem, we defined a label predictor to be the fake news detector and a domain classifier to be the dataset classifier. Here are the four datasets we used in our method. The first one is Fake News Net. It contains two types of fake news, politics and gossips. Fake Health is a public dataset related to healthcare. It is separated into two groups, Health Story and Health Release. Health Story are collected from news media, while Health Release are from various institutes, including universities, research centers, and companies. Co-aid and recovery are two datasets associated with COVID-19. While co-aid only covers topics related to healthcare, recovery contains various topics. Observing the statistics of the four datasets, we can see that all of them have more samples of real news than fake news. Especially for co-aid, this dataset is very imbalanced. With the four datasets collected, we propose our method. In this diagram, we utilize two types of information, news content and social context. For social context, we choose to exploit users' information who tweeted the news and the tweet itself. For the embedding of both of them, the raw inputs are fed into a pre-trained BERT model following a max pooling to have a 1D representation, which serves as a feature extractor. The two classification heads are the domain classifier and the fake news classifier. The domain classifier tries to unlearn the dataset bias, and the fake news classifier tries to increase the detection performance. Applying the methods on the four datasets we have shown, which was trained on them as a whole, here is the result on the test set of Fake News Net. In a table, lambda represents how much the domain classifier influences the feature extractor. In other words, how much reverse gradient it passes to the feature extractor. If lambda equals to 0, the domain classifier doesn't have an impact on the feature extractor. If lambda equals to 1, the domain classifier will have full impact on the feature extractor. On the second column, the symbol N, T, and U represent news content, tweets, and users, respectively. The four metrics that shown were obtained by calculating separately for the two classes and then averaging them. For this dataset of Fake News Net, we can see that the news and users together have a better performance than the news and tweets together. The best performance were achieved when lambda is equals to 0.7. We didn't use N, T, and U together. The reasons are twofold. First, the BERT model was trained with a pair of sentences separated by the SAP token, and it might perform well with 3 or more sentences. The second reason is the memory constraints. The news contents is usually long, and one piece of news can have many tweets and users associated with it. So to be able to fine-tune the model, the sequence length has to be limited, which means we would lose some information by cutting the tail of the sentences. In this table, we listed the best performance on the 4 datasets. We can see that Fake News Net and Recovery have relatively high performance, and Fake Health achieved the worst performance. For co-aid, as it is a very imbalanced dataset, the precision is pretty high, while the recall rate is very low. We can also see that the best performance were not achieved by the same lambda or the same context. To investigate the reason behind the results, we took a detailed look of how the data were being labeled, as we know that quality of labels are very important in supervised learning. In this table, we observed that fake news net, co-aid, and recovery are all labeled mainly according to the source website. The annotators assume that the news from reliable websites are real and news from unreliable websites are fake, while for the fake health dataset, each piece of news were being reviewed by experts from healthcare. They gave a score from 1 to 5 according to 10 criteria, which is much more strict than the other 3 labeling process. The annotator of this dataset labeled a piece of news as fake when a score is less than 3 out of 5. However, the website itself didn't claim that the news is fake. That's why we think this might be the reason for the fake news detector to perform badly on the fake health dataset. Based on the results and analysis, we have the following conclusion. The main adaptation can help the detection performance. However, it is difficult to define the boundary of fake or real, causing different datasets to have different labeling process, which could confuse the fake news detector when using multiple datasets and thus make the detection performance unpredictable. In future work, we still have a lot of options to explore. For content, we have not used the information from images of the news, which can be utilized in different ways. For example, we can extract visual features directly using networks. We can also seek forensic traces of images to check if it was tampered or copied from somewhere else. We can also convert image into text and compare with the text content to see similarities between them. For the text content and its associated comments, we can explore different representations to deal with long sequences. We can also seek for its external information through entity recognition and knowledge graph. Additionally, tweet-retweet network, propagation network, and users' interaction network in the social media can also be valuable for the fake news detection. Thank you very much for your attention.